Okay, let's look back at the last topic. So it's about understanding limits and somewhat trickier than others. Okay, so remember that the definition of continuity might look a bit complex, but really that's not it. It is a way out. Okay, here's the definition of continuity right here on the right. So it is at the same time understanding of continuity through limits, if we understand limits to the degree that we do. But on the other hand, when we need to compute limits, it is if we know that the function is continuous, that is the end of it. We don't have to do any work. So if you once again look at this definition and read it from right to left, then if you know that the function is continuous ahead of time, to compute the limit, you just plug in the value. Okay, so this is the function is bad, and not only because it's hard to compute the limit, but not only because it's discontinuous and has this gap, which leads to catastrophic outcomes, no matter how small the error is. But also it helps us to, if we discard those, put it out of the way, we can compute limits in a very easy way. So unlike this, so let me once again remind you what this is. So limit, say, x squared, x goes to 1 to 2 is equal to 2 squared. So this is an example. This is 99% of the time, or ideally, you're gonna be computing limits like that. So you see what has happened. I just plugged in, I replaced x with 2. So instead of saying x approaching 1, how about I just say x is equal to 2? And that's the answer. So if we are able to stick with continuous functions, the limit is really not an issue at all, at least for so far. And then whenever it's actually the big point, must be a big reason why we cannot do this. Okay, so that's example on left is exactly when this is not available. The function is not continuous to begin with. If you look at the top, it's undefined at x equal 1. So that's the problem right away. Denominator has division by 0 if we plug in x equal 1. So that plan on the right cannot possibly work. Okay, so what is then? Then of course we put ourselves by design in a position when this is hard, but we try not to do that with no reason. This one actually, the example, especially fractions, that's what's going to be we're going to be dealing with in the rest of calculus. I mean all calculus, and that is the rate of change. So imagine that x is our change, and we're changing from in numerator changes. Both numerator and denominator might represent change, and we're looking at the rate of change, and the rate is the ratio, and then you end up with you're looking for instantaneous rate of change. Okay, so that is inevitably is a limit, and unfortunately the denominator turns into 0 routinely, not by design, but it just happens because that's what it is. But still, that what's on the right is the answer frequently, because that's how we actually resolve this, and that goes all the way back to Newton, how to resolve this problem of division by 0. Division by 0 is good because it is usually simply means that we have infinity, though, just like that example on the left. This is an indeterminate expression because numerator is also 0. Not that at the top, but rather this example at the bottom. At the bottom, as you can see, it's indeterminate, 0 over 0. So that is the typical situation when the change of x and change of y is change of numerator and denominator is the same, is both of them going towards 0. Okay, so and then let me scroll up. This is what we want to accomplish, and most of the time that's how we do it. Looking at indeterminate expression such as this, and then we invoke algebra half of the time or more, actually, in order to deal with it. That's what Newton did when he discovered that he needed to evaluate limits with indeterminate expressions 0 over 0. So what he discovered, just from algebraically, you can make a very easy algebraic trick, and indeterminacy is gone, and you are right here. So that what I just did on the right, this substitution, this is the substitution works here. So this is the function is, this one is continuous, and so evaluate the limit by substitution. That's what happened. So we replaced x is approaching 1. We replace it with x equal to 1. That's what substitution is. So that difficulty of understanding quantities, certainly a limit is a quantity, but we understand it where it comes from. It comes from kind of a dynamic process. We're saying x is approaching 1, so it's not just one number, it's kind of we're getting there somehow after infinitely many steps. So remember those sequences. It takes infinitely long to get there. But if the function is continuous, we don't have to worry about it. So all we have to do is just reduce our situation, which is discontinuous, right? That's on left. We have the division by 0. If we can, through algebraic tricks, get rid of that situation, and we end up with the continuous functions that we evaluated by substitution. So that's what we did with sequences. Remember, you might remember this one, n squared plus 1 over n squared minus 1, and what do you do with limit when limit is going to n going to infinity. Remember also we did the algebraic trick, and it's exactly the same situation, even though indeterminacy is different. So that was infinity over infinity, this is 0 over 0, but it's the same story. You apply algebra and then so that indeterminacy goes away. Okay, so that is the plan. Not really that hard. It's just algebra might be you might have to think about it for a little while. This one, I think somebody actually suggested that right away. What do we do algebraically with that expression, this expression, in order to get rid of the denominator? And the answer is factor and cancel. That's what we did, and then suddenly we are in a very good position, because there is no question that the limit of x plus 1 when x goes to 1 is equal to 2. Okay, the difference is between where we ended up and where we started is this. So let me plot the function x plus 1. Looks like this: y equal x plus 1. That's where we ended. But where we started, the function is slightly different. It's almost exactly the same, except there is a hole in it. It's undefined at 1. Okay? So that's the starting point. X squared plus 1, y equal x squared plus 1 over minus 1, minus 1x minus 1. Okay, so that's the difference. The graph is almost identically the same, except for the missing hole. And then through this analysis, we realize that it doesn't really matter. The behavior of the function in the vicinity of this point, which is 1, is that y approaches 2. Okay, so this is 2. Okay, so that's what we have discovered through this algebra. Okay, so in that's most of the time is what we do with limits. We simplify and to find where we are. Okay, so you can think about it, well, just as in quick examples of what might come up. X cubed minus 1 over x minus 1, limit, once again, x goes, well, how about I put a 9 here? Hold on a second. What do I have in mind here? As an example, instead of going through the whole thing, limit x goes to 3, x cubed minus 27, x minus 3. So what do we do with this one? Again, we have division by 0. So what do we do? Yes, it's sometimes a different algebra, but half of the time it will be factoring. How you factor it is a difference of 2 cubes If you don't remember the answer, that's fine, but you certainly can find it in any book, usually inside the cover. Formulas. The difference of squares you probably should remember. Difference of cubes if you don't remember right now, that's fine. But it certainly factors. And maybe somebody does remember how you factor difference of cubes. It's actually the sum of things. X squared plus 3x plus 3 plus 9. Yeah. And then we cancel again. It is not by design. Well, let me finish the example. Okay, at this point we just say, well, and that is a standard way of doing it once you went through algebra. So this is the algebra step. Once you went through algebra, you end up with a function. Now you say magic words. The function is continuous. Well, I already did over there. So substitute. That's it. And so, well, and you substitute. And substitute meaning this x minus 3, x converging towards 3, I replace it with x equals 3. So that's the substitution. We substitute x equals 3. Okay, so I have 3 squared plus 3 times 3 plus 9. Okay, so that's the end of it. Sometimes it's more complicated situations, and as needed, we'll deal with them. At this point, let's just learn the lesson that 0 is 0, which we're going to see a few times, is not the answer. It's also not the end of the world either. So through algebra, you can find what's behind it, and the answer could be anything. It's indeterminate. 0 is 0 is indeterminate, so whatever is behind it could be literally any number could be behind it, as well as could be still not existing a limit. It's possible. So 0 is 0 at the top, the answer is 2. 0 is 0 at the bottom, the answer is whatever it is, 27. Okay, so there you go. So the magic words is the function is continuous, and then you're done. So you have to just make sure that the function is continuous. But at this time, you find out that the functions are continuous through evaluating the limits and then making that list of functions that we know to be continuous bigger and bigger. Okay. Fortunately, the list is really long. It just takes some time to get the whole thing. But all polynomials are continuous, for example. Okay. So let me state that just to somewhere to get started. So. Fact number 1, all polynomials are continuous. Okay, so if you see a polynomial, and we just did it twice, plug in the value of your limit, you're done. Okay, so they don't have any holes in the domain. They don't have any infinities here and there, so they're nicely behaved. The rational functions what are rational functions, by the way?
Is it square root?
No.
Anything that doesn't have an answer of an imaginary number?
No. The way to remember is this.
Ratio.
Yeah. Yeah. So ratio of what?
Fraction.
No, it is ratio of 2 polynomials.
Oh.
Ratio of 2 polynomials. So we just saw it. So this is rational. That is rational. So these are rational functions. Of any degree polynomial numerator, any degree polynomial denominator, you have a rational function. Okay, the rational functions are also well behaved, but So it's like P over Q, and both of them are polynomials. Both of them are polynomials, but remember then the Q might be a problem because it's polynomials might have zeros, which means that the denominator might be 0, which means that we might divide by 0, which means that simply the domain might have holes in it. Okay, so here if Q of x is equal to 0, then x is not in the domain of my function of f. Okay, so that's to know about polynomials. About rational functions is that the zeros of the denominator are the holes in the domain. Okay, that there is nothing else. Otherwise, the domain is everything. So okay, so that is what functions are. This is what creates a problem. But if we stay away from those holes, we are fine. Okay, so all rational functions are continuous on their domains. Okay, so the problem with those two examples was that we by design we picked points where the function was undefined, and that's why we cannot just say it's continuous, because it's not. But you can easily think of this. I could just take the function that we just looked at, x squared minus 1 x minus 1, and what if I'm considering limit as x goes to 2? Okay, so I can apply this idea over here and say, well, first of all, this is rational. Then next step, I find the domain. You don't really need to find the domain. You know that x equal 2 is the one that we care about, and you just ask yourself, is 2 in the domain? Is it? Yes, it is, because there is no division by 0. So then use fact number 2, and what? Substitute. And substitute the value of x equal 2. X equal 2 substituted into the function will be the value. So I have x squared minus 1. Let me write it this way. This is how you sometimes write substitution. So you repeat the expression, and then you draw a vertical line and indicate what your substitution is going to be. And then you carry out the substitution. 2 squared minus 1, 2 minus 1, 3 over 1 is equal to 3. Okay, so that is an example of how things might work out. And in fact, if you think about this exact function, it has only one problem point, x equal 1. The rest of them are fine. Because, well, that's what think about polynomials. They only have as many zeros or less than its degree. So in this particular case, the polynomial has degree 1. It has only one zero, denominator that is, and therefore the domain is everything with one exception. Okay. Unfortunately, that is the exception is actually the point of interest of as we get to study the derivatives. Okay, so there are some other examples of this behavior. All polynomials are continuous, so all rational functions are continuous on their domains. Well, as an example, say x over x squared plus 1. What's the domain? All reals, yeah. So as you can see, we are good. So this function is all continuous everywhere, even though it's a rational function. It does not have necessarily to have some problem somewhere. Okay, so let me point out as we are doing this is what this expression might or will in fact we're going to be dealing with. It is, as I was saying, it is a rate of change. Of change. So why do we have to concentrate on these limits out of all possible limits that are actually bad for us? They're hard to compute. I mean, if function is continuous, just plug in the value, you're done. And yet we pick one like this. Well, there's a reason for that, because we're going to study derivatives. And the derivatives are rates. You have a fraction, and it is, in fact, what we really care about. Limits in general are important, but especially these kinds are especially important. Okay, so this is, if we are concentrating on, we are looking at the function y equal x squared, and we are looking at one particular point at x equal 1, okay, then this is what we're looking at. We're looking at the change of, and suppose we're, say, here. Change of x is x minus 1. Okay, so we are concentrating on a point x equal 1, and then we make a step off it towards a point, say, x. Okay, and then see what happens to the change of the function. Change of x is x minus 1. Change of y is, well, let's see what it is. So x squared, 1 squared, this is 1. Okay, what is this?
X squared.
This one is x squared, that's right. So then the change is x squared minus 1. Okay, so the red one, a change of x. The green one is the change of y. And we're interested in the rate of change, how fast y changes relative to x. Okay, so, and that's where this function comes from, x squared minus 1, x minus 1. Okay, so it is as if we're talking about velocity. So if x happens to be time, then and y is location, then we have in the numerator, what is the meaning of change of x? It is a time interval, time that has passed, how much time has passed. Okay, so that's the denominator, x minus 1, and then the numerator is the change of location. Okay, and so that is x squared minus 1. Okay, and so if you divide one by the other, the change of location over change of time, you have your velocity, except it only works out the way it is when your velocity is constant, but it's not. As you can see, we actually are speeding up, and that's where the problem of instantaneous velocity comes up, and you can only evaluate it as with a limit. So x going towards 1. So we make this change of y shorter and shorter and shorter, and see what's happening to y. It also getting shorter and shorter and shorter, but what is that in the end? What is that in the end? What is the limit of it is? And that's the big question. And as you can see, we cannot figure it out without the meaning, figuring out what the meaning of a limit of such a nasty thing is. Well, it's not really that bad. As you can see, a little bit of algebra, and we get through. There are, in the same venue, there are other limits. So this is one example of a kind of an important limit, but there are more limits, more famous limits. One famous limit of the same kind is sine x over x. X goes to 0. Okay, so it's actually very similar to what I just explained, except we're looking at sine instead. So the graph looks like this. So that's y equals sine x, and then we want to look at the behavior at 0, and once again we're making one step to the right with x, and see from 0 to x, and then that produces a change of y right here. Okay, so that's the change of y. Okay, so and then we have once again the fraction. The rate of change will be of sine, rate of change of y equals sine x at x equals 0 is a fraction, change of x in the denominator, so it will be x minus 0, and the numerator is sine x minus 0. Okay? So once again, change of y, or change of x. Okay, and we end up with sine x over x. Okay, and then so that's the where limit comes from. You can certainly carry out this. Let me take a look. I actually might have an Excel file here. Sequences. Sine. There's one of these many. There's too many. Sine n x. Yeah, I just accumulated too many, and now I can. This is one way. These are sequences. Well, it's really not that hard to reproduce, but you can actually guess the answer. That's another. Looking at numbers is a good idea to find out what the limit is. You just compute this fraction for small and small values of x. Okay, but you can guess before we do that. Can you guess what the answer is?
I think it'll be the sine curve, except it'll just get smaller and smaller to a certain value, maybe?
Well, yeah, but look at it will be exactly what is that certain value. If you can imagine looking at this graph, and what is the meaning of the limit as x goes to 0? What it means that we're zooming in closer and closer on the graph. So you can see that the graph as you zoom in will look more like a straight line. That graph that I plotted will look more like this, more and more. And in that particular case, as you can see, the rate of change will become very clear. This is x, and this is y, right? So, well, that will be the meaning. Turns out the answer is 1. Okay, so it turns out that this whole thing goes to 1, so the change of x and the change of y is the same, roughly, at the limit. You can certainly detect this from the graph of the function, but you might remember this function. It's that nasty the function that well, the function is not nasty, but well, x. No, it's actually looks fine, but it is undefined at 0. So the issue of evaluating the limit of a function that is not continuous, So plugging in, you just, in fact, if you plug in 0 into both values, I have 0 over 0, right? So that's not. That's certainly an indication that the function is not continuous to begin with, because there is division by 0. And secondly, that the only way to handle it is through some manipulation. This unfortunately, it's difficult with trig functions. Manipulation that we are good enough with algebra to do things like that. Factoring and then not like this, but like this, factoring and then canceling. It's not going to work with trig functions. So actually, to prove it beyond numerics would require some looking into trigonometry. Looking at trigonometry and like a circle, and this is x, and this is sine x. This is sine x over here. So x is the angle, sine x is well, you end up with a right triangle, and the cosine x is the horizontal length, and the sine x is the vertical. Okay, so this is sine x, and this is cosine x. Okay, and then that you have to look at this triangle very carefully in order to demonstrate that indeed you're going to end up with 1. Okay, and in fact, well, let me write them side by side. The other limit, so the answer is 1, and the limit of, well, cosine x over x. The same exact situation, except this time the graph looks quite a bit different. it looks like this. Cosine looks like this. Okay, so but we're looking at the same question is we step x to the left. We are looking at what's happened to y. Well, let's see what happens to y. Y goes down like this. Okay, if we step to the right from 0, then the value of y goes down. But you can guess what the answer is. Can you guess what the answer is? Well, compare the change of x, the red one, to the change of y. Over there, they are similar. They're similar in size. In here, look at how y is small. How small the value of y is in comparison. Well, I'm not sure if it is entirely obvious, but if we zoom in, once again, what if we zoom in, then this is what we're facing. This is the graph will be very flat. Okay, so then the change of x might be this, but the change of y will be tiny, like this. So the answer is 0. Okay, so once again, that requires some trigonometry to figure out why this is the case. Yeah.
Can you just think of the unit circle whenever you do that?
It is the unit circle. I'm sorry. What I drew didn't look like a circle, but I certainly.
I know what you meant, but I've never seen it like sine x is the y-axis and cosine x. I've just seen them as inside parentheses, So is it cosine x is your x value on the unit circle, and sine x?
Right. Yeah. That is actually the definition of the sine and cosine, apart from trigonometry that you faced in high school. Probably it's more like in terms of triangles. And here the triangle is really not as important anymore, right? So this is it's still there, but what actually matters is the angle, and not only the angle of x, but more like we are thinking of x as a rotation. So we're starting right here on the x-axis. We start this way, and then we start to rotate it. And x is the rotation.
So if we said both of those, sine x over x and cosine x over x, as x approaches 2,
x approaches 0? X approaches 0?
As x approaches 2, both of the limits would be square root of 2.
Well, x approaches 2 in radians.
I messed that up.
For 45 degrees you're talking about?
Yeah.
Right, yeah.
Okay.
So the angle will be 45 degrees. Sine and cosine are clearly equal to each other. Well, we want to know, actually, if you're only talking about sine and cosine, it is the function is actually continuous. So that's another fact number 3, if you like. Sine and cosine are both continuous functions. Unfortunately, that's of no help to us because we divide by x and we have a problem at 0. Okay, so that really doesn't help us a lot. So you have to actually analyze. You produce from a continuous function sine, we produce this fraction, which is not continuous anymore, unfortunately. But that's because we're not studying continuity of the function anymore, sine. We're studying its rate of change. Okay, so in other words, the angle, how it crosses the x-axis. So it crosses at 45 degrees, as a matter of fact, here. Okay, and it crosses at 0 degrees. In other words, it's horizontal here. Okay, and so because it's not a straight line anymore, to figure out the angle, you have to go with a limit because as you can see, the angle changes. Look at the graph of sine. It goes this way and then small like this. So how does it cross the x-axis? It's hard to tell. You can do it only one point at a time, and then you have to use the limit. So that's why we do it this way. So maybe I'll do that next time, the sine over x. Well, let me do it now. So I'll go with the Excel and just create a little. No, more. There are a bunch of them here, but I just can't, it's hard to find now. Okay, so let's see how we're going to do it. So the function, this will be, say, n, x, and y. Okay, y, this one, x, will be computed. How about we go with one sequence of, well, first of all, do you remember what the graph of this function is, of sine x over x?
It's 45 degree.
Sine x over x. No, 45 degrees is the, it is 45 degrees. We're not using degrees anymore. So in fact, it's the slope. The slope of 45 degrees is 1. Right, so this line is in fact 45. It is actually y equal x. So that's the slope of the line that we are after ultimately. And so that's the meaning of the number 1. It is the slope of the line at that point. But the sine x over x, well, I guess we just need to plot it. Well, let's plot it. It probably won't be that easy, but let's do it because it's still useful. Okay, so let's say, let's go down, and I will start with, say, well, 1, and this one equal this plus 1. Okay, so this one will go down 1 over n, just as we did before. Okay, so x will be 1 over equal to 1 divided by n. Okay, so we're going with a sequence as before. X's are going towards 0. Okay, so this is what I'm talking about. So this is what I'm talking about. Okay, so you can see how things are going towards 0. So this is just the how many we've got, and what number? That's so stupid. Anyway, so this is how many we've got, and then we computed x's, and you can see how they're getting smaller and smaller. Now we're computing y's. Okay, so that will be interesting. So it will be sine x over x. So sine of this divided by the same thing. Okay, you see it? Sine x over x. Okay, so let's see what's happening. And you see what's going on?
It's getting closer and closer to 1.
It's getting closer and closer to 1. So that confirms that numerically that the limit has got to be 1. For a complete picture, you probably would have to plot the graph of the function. So let me do that. So I have a few minutes left. So this is just the limit itself, limit at 0. I wanted you to see that where it comes from, because this is just one sequence. Technically, to compute the limit, we need to look at all sequences, not only 1 over n, but say 1 over n squared. Okay, and certainly it's not hard to see that the result will be the same. But I wanted to try to plot the function. Say, okay, let me put h here, 0.1. X is equal to starting with 0 here, and this is equal to this plus h, which is R2C6. Okay, so I will be progressing from 0 to 0.1 at a time. Okay, and then I will be computing sine x, and then next time I'm going to plot it. So it's equal to let's start here, is equal to, once again, sine of this over that. Okay, and okay, so let's plot it. Okay, so well, that is the function that we have plotted. There is really nothing special about it except we cannot get too close to 0. Okay, so let me plot it. Okay, so that's the data that we have plotted it. So where is the challenge really? The challenge is the function is not continuous. So if I try to start at a lower and lower location, here I'm starting at 0.1. What if I start 0.01? Okay, let's keep doing it. It's still working. Okay, I'm good for it. Interesting. I want to see when Excel breaks down. Oh, look at it. So it doesn't break down still, but that is really confirmation of the limit. The starting point is very low. It's 10 to negative. It's like 9 zeros. Decimal point in 9 zeros, and that's why when we move away from that, there is really no change of the value of the function. And well, that's to be expected. I guess it just confirms the result. There's a division by x. Even though there is a division by x, look at it. We really did division, and the number is very small. It's still being able to handle this kind of stuff. Okay. I put. No, it's still working. Oh, okay. I was hoping, or not hoping rather, I was afraid it will break down because then you divide by a number that is too small. But you see, it matched with the sign is in the value of the function. The numerator is matched with the denominator, so it does not compute one separately from the other. Two very small numbers, and then that's very hard to handle. But they tweak it. There's some computational tricks that they make so that you don't have to deal with numbers that are too small or too large. If they're canceling anyway. Okay, so one small number sign and the other small number x, which is in the denominator, numerator and denominator, and they just that cancels out, and you end up with what do you know? You end up with 1 no matter what. So that certainly confirms our suspicions. You can replace it with cosine. The result will be the same, except it will be 0. So, well, let me do it. So I put cosine here instead. Okay, pay no attention to this. What happened? What happened? I don't think I did it right.
I think it's just recognizing.
Oh, yeah, no, the correct formula cosine minus 1. Okay, cosine minus 1. I messed up. Sorry about that. Minus 1, like this. Okay, so they're all 0. So once again, the function is not that cosine minus 1 over here. Okay, cosine minus 1 is the value. Look at the value of y. This is 1. So if you want to look at the change of y, it will be cosine x minus 1. Okay. All right. So the convergence has been confirmed. The methods of computing these will develop. Let's state what I just promised to state, and that is the fact number 3 to be used. Sine x and cosine x are continuous. These 3 classes will be enough for now. But then the step that we have to make is still the same, and that is just like with limits. Before it is the continuity versus algebra. Okay, so continuity and algebra. And the behavior is very, continuity behaves well with respect to algebra or vice versa. So for example, the sum of 2 continuous functions is continuous. At x equal a is continuous. At this point, for the time being, we are concentrating on one point at a time. So we are just have a function. There are infinitely many points, but we really want to look at one at a time and see, is there any cut there, or is there some wild behavior that ruins everything. So that is it follows from the sum rule. So the sum rule of limits that we know applies, and the sum of 2 continuous functions is continuous. Okay, and the difference too. and the product and the quotient. With the quotient, however, there's only one to worry about, is division by 0. So provided the denominator isn't 0. The denominator isn't 0 at x equal a. So that is the caveat that the quotient rule came with. It came with limits of the quotient is the quotient of the limits, except when you have the limit of the denominator is 0. Okay, then all bets are off. It's the same thing here. You certainly can divide by function x squared plus 1 over x minus 1. Same story as before, even though both of the functions are continuous, but the denominator is 0 at 1, and then it means that there is no continuity at that point. Okay, so we'll continue next time.